Welcome to Basic Environmental Sciences. In this session, we'll be covering the formation of soil. Soil is a crucial component of the Earth's surface, composed of organic matter, minerals, gases, liquids, and living organisms, all working together to support life. We refer to this as the pedosphere, the Earth's body of soil. It plays four key roles: providing a medium for plant growth, storing and purifying water, offering a habitat for organisms, and modifying the Earth's atmosphere. Soil is formed through the process of weathering, where parent material breaks down over time. Mechanical weathering happens through forces like wind, rain, ice, and heat, while chemical weathering involves acids and moisture. This breakdown releases minerals, nutrients, and materials like silt, sand, and clay, all of which contribute to the creation of soil layers. Soils can be classified into four basic types, each with distinct characteristics. First, sand has a gritty texture and drains quickly, making it ideal for plants that thrive in dry conditions. Next, we have clay, which consists of fine particles and retains water well, though it can compact easily and drain poorly. Loam is considered the ideal soil type for agriculture and gardening, as it's a balanced mix of sand, silt, and clay, providing good drainage and fertility. Lastly, silt retains moisture better than sand and is more fertile, but it compacts easily, so careful management is needed to prevent this. Understanding these soil types helps in selecting the best soil for various agricultural or environmental purposes. Soil is made up of four main components, namely mineral matter, organic matter, water, and air. Mineral matter, which includes sand, silt, and clay, makes up about 45% of soil, while organic matter, such as decomposed plants and roots, accounts for 5%. Together, they form the solid portion of soil, making up 50% of its structure. The other 50% consists of pore spaces filled with air and water. Ideally, 25% of soil is water and 25% is air, which creates the perfect balance for root growth and nutrient absorption. These components work together to provide the necessary conditions for plants and other organisms to thrive in the soil. This slide explains the impact of water-filled pore spaces on soil respiration and porosity. When soil has more than 60% water-filled pore space, it accelerates processes like soil respiration and nitrogen transformations, such as ammonification and nitrification. However, the limited aeration at this level of moisture can inhibit soil microorganisms, reducing their ability to perform these vital functions efficiently. On the other hand, when pore space is more than 80% filled with water, soil respiration drops to minimal levels, and denitrification becomes dominant. This can lead to nitrogen loss in the form of gases, increased emissions of greenhouse gases, reduced crop productivity, and a greater need for nitrogen fertilizers. Understanding these moisture thresholds is key to optimizing soil health and managing agricultural productivity. This table outlines key parameters and formulas used in soil sample analysis. It includes calculations for the volume of soil cores, gravimetric and volumetric soil water content, soil bulk density, and particle-specific gravity. Additionally, it covers pore space, solid material, and both water-filled and air-filled pore spaces, all of which are crucial for understanding soil composition and behavior in various environmental conditions. This example provides a practical application of the soil analysis formulas. Given a soil core with a diameter of 7.5 centimeters and height of 10 centimeters, we are tasked with calculating several key parameters, including the volume of the soil core, gravimetric and volumetric water content, bulk density, pore space percentage, and the percentages of water-filled and air-filled pore space. These calculations help to understand the soil's physical properties and its suitability for various uses. In this slide, we begin by calculating the volume of the soil core using the formula for the volume of a cylinder, pi r squared h. With a diameter of 7.5 centimeters and a height of 10 centimeters, the soil core volume is calculated to be 442 cc. Next, we calculate the gravimetric water content, which measures the amount of water in the soil relative to its dry weight. Using the formula, mass of moist soil minus mass of dry soil, divided by mass of dry soil and multiply by 100, we find that the gravimetric water content for this soil sample is 19.8%. In this slide, we continue with the calculations for soil properties. First, we determine the volumetric soil water content, percent, which represents the volume of water within the soil core. The formula for this is volume of water divided by volume of soil core and multiplied by 100. To get the volume of water, we divide the mass of water by the density of water. In this case, 685 g minus 572 grams, divided by 0.997 grams per centimeter cubic. The result gives a volumetric water content of 25.6%. Next, we calculate the soil bulk density, which is a measure of the mass of oven dry soil per unit volume of the soil core. The formula is mass of oven dry soil divided by volume of soil core. In this case, 572 grams divided by 442 centimeters cubic equals 1.29 grams per cm cubic. This bulk density value tells us how compact the soil is, which influences root growth, water movement, and soil structure. To calculate the percent pore space, subtracts the volume of soil particles, calculated by dividing the mass of dry soil by the specific gravity of the particles, from the total soil core volume. This difference is then divided by the total core volume and multiplied by 100 to give the percentage of the soil that is made up of pores. In this case, 51.1% of the soil core volume is pore space. For percent water-filled pore space, as it uses the volumetric soil water content directly, 25.6% of the pore space is filled with water. Finally, percent air-filled pore space is determined by subtracting the water-filled portion from the total pore space. In this case, the calculation shows that 25.5% of the pore space is filled with air. Thank you all for your attention. I hope the insights on soil formation and characteristics of soil are helpful. I look forward to engaging with you in future sessions of the course.